Section 6.4 is called dot products. It's like a special way to multiply vectors together. Now there is vector multiplication, so it is something a little bit different. The main thing we're going to see this used for is work in physics. So for those of you taking physics next year, work will be something that you'll deal with quite a bit. So this will be something that comes up in that process. So kind of the classic example is pulling a sled. I'm going to use this stapler as my sled for the example here. And the string, that's the force vector, because wherever I pull, it'll be in the direction of that string. Now if I want this stapler to move this way, it probably makes sense that I want to pull that direction, which is pretty easy if I pull like that. Now, in reality, when I'm pulling a sled, I'm standing up and the string's going to kind of hang behind me, so it's going to be kind of at an angle. And what's going to happen is a lot of the force is going to be the way I want to go, but some of it's going to be wasted upward, and the sled's maybe going to lift off the ground a little bit, which for a sled, that's okay. But if we're pulling something really heavy, we got to really be aware of how much force we're wasting upward. And the more I pull up, the harder I've got to pull to make this thing go forward. It will go forward, but at this point, most of my effort is being pulled up. And eventually, if I pull it straight up in an attempt to pull this way, well, common sense will probably tell you that's just not quite going to work out. And then if I start pulling backwards in this direction to pull that way, that's definitely not going to work out. That's some of the stuff we'll get into tomorrow. But that's sort of the way to think about it. It's the force is in the direction of that string, and you want to come up with a compromise if you want to pull as much as you can in this forward direction, but to walk comfortably, you got to pull kind of upward as well. And that's what we got to look into. How much force is in the direction we want to go, and how much is wasted? Because all we really care about is how much force is in this direction we want to go. So since it's not really practical to pull a sled straight down at the ground level, you're going to be pulling at an angle, or at least an angle to horizontal. But the thing is, you want the sled going across the ground, and you're going to make that happen by pulling at an angle. Okay? So really the only force that helps you get the sled across the ground is whatever force is in that direction. So adding this force in the x direction vector, it's parallel with the distance vector. In fact, we can draw it right on top, and that's fine. Because in the end, what I'm going to do is multiply the force in this direction times the distance I've moved in that direction. And that's how I'm going to calculate work. So for now, I can kind of ignore this d vector. I know it's kind of weird, but for now, think of it this way. This is distance in something like feet. This is force in something like pounds. They're completely different units, so really these two triangles can exist separately, but kind of layered on top of one another, if you want to think of it that way. So I really need to figure out what this force in the x direction is. So let me kind of show the overall goal. Work is force times distance, but I need to only know the amount of work done in this direction, because that's where the sled's going to move. It's going to move that way. So work done any other direction really doesn't show me anything, because the sled doesn't move that way, or doesn't move any other way but here. So horizontal is all that matters. So the force applied will be this force in the x direction times the distance it moves. So I'll go ahead and put some little vector hats on those values. So to figure out force in the x direction, well, I know hypotenuse, I know an adjacent side, and I'm going to want to set up a cosine equation. So force in the x direction divided by the overall force is the triangle, is the cosine of the angle. So the force in the x direction is the overall force times the cosine of that angle. So I'm going to substitute that in, since I know that's what force in the x direction is. So work is the overall force times the cosine of that angle times that distance vector. And that'll end up being the formula you use. If you want to do a dot product between two vectors, if you've got that angle between them, you just take the magnitude of each vector and multiply by the cosine of what's between them. So here's that idea in a more general form. You read this A dot B. So it's like multiplication, but it's like a special type of multiplication. It's multiplying the vectors in one direction, not necessarily using both directions, just one of them. So A dot B It's equal to the magnitude of A times the magnitude of B times the cosine of the angle between. So that is the first formula that we're going to use for the dot product. We're going to come up with a second one here in just a minute. So just to clarify again, dot product is the amount of effort in one particular direction only. And think of cosine as the percent of effort needed or given in that particular direction. Because we talked before about how sine and cosine are just the percent of the hypotenuse in a particular direction. So that's really all this is. The cosine of an angle is just the percent of the hypotenuse in that adjacent direction. So let's practice the skill now. Let's do an example where we find u dot v, these two vectors and that angle between them. So all you really need to do is find the magnitude of the two vectors, which is conveniently given to us. We've already got magnitude of u and magnitude of v, times the cosine of the angle between them. And we had to put 70, so I know 7 and 10 make 70. So 70 cosine 37 is about 55.9. We'll go with that. So my dot product is 55.9. And we didn't get any units, so we don't have to put any units in our final answer. Now, so far we've explored how you can get the dot product from taking the magnitude of two vectors and the angle between them. But there is another way that you can figure out your dot product when all you really have are coordinates and you don't actually know the magnitude of the vectors. So let's kind of go through a derivation process, figure out what that's going to be. What I'm going to do, I'm going to add another vector in here, and we'll call it C. And it's just a third vector that's the result. If we go two different directions, it's the result. If you want to get technical, it's the difference in the two vectors. But for now, let's just say it's the distance between the endings of those two vectors. So something I know to be true from law of cosines is that the magnitude of C squared will equal the magnitude of A squared plus the magnitude of B squared minus twice the magnitude of A times the magnitude of B times the cosine of the angle between. So that's just law of cosines. Something I want you to notice, or something that should stand out to you kind of right away here, is there's the first way to find dot product already kind of worked into all this. If you look right here, that is our dot product formula. So I'm going to leave that piece alone as I go through deriving everything else, because that is the dot product formula. I want to solve for this whole thing. I want to get this equal to something so that I've got a second way to find a dot product. And using these in combination can help you find all sorts of things on the homework. So the next thing we really need to figure out are what are these different magnitudes? And what I'm going to make this easy, I'm just going to say we start at the origin. And I'm going to call this point AB. I'm going to call this point MN. The letters I use are completely arbitrary. It's just to make it convenient and easier later. So let's figure out some magnitudes if that's what we call these things. So first up, let's find magnitude of A. Okay. Well, it's really just the distance formula. It's the distance from this point to this one. And that's going to end up being the square root of A minus 0 squared plus the distance of B minus 0 squared. Now, I'm showing you a lot of extra here just to make sure I cover everything. So really it's a square root. And that's going to be A squared plus B squared. You simplify it down. So magnitude of A squared plus B squared. Now magnitude of B is really similar, so I'm going to kind of shortcut that one. You'll end up subtracting n minus 0 and squaring it. And you'll end up subtracting n minus 0 and squaring that. Add the two together. That's your magnitude for vector B. All right, vector C, a little more involving, but not too bad. It's going to also be a square root because it's distance formula or Pythagorean theorem. And we're going to end up, doesn't matter which way we go, we can do A minus M or M minus A. I'll just say A minus M squared plus B minus N squared. Really, the only thing that's important is if I started with A, then I need to start with B. That's the main thing there. So there we go. There's our different magnitudes for A, B, and C. So at this point, I'm going to go ahead and plug some things into this law of cosines formula. I'm going to leave this alone because that's the dot product formula right there. So magnitude of C squared. Since I'm going to square this, the square root's going to go away. So I'm just going to have A minus M squared plus B minus N squared. And in kind of similar logic, I'm going to square the magnitude of A. So this square root's going to go away. I'm going to square the magnitude of B. This square is going to go away. So I'm just going to have over here A squared plus B squared plus M squared plus N squared. Magnitude of A squared, magnitude of B squared. And I'm going to leave the rest of it alone because I want to keep that dot product formula in there. So minus 2 AB cosine theta. Now I know there should be the brackets around those, the A and the B, but hopefully we get the idea. And I'm going to just, so I don't have to have so much stuff to write, just clutter. All right, let's do a little bit of expansion. We're almost done now. A squared minus 2AM plus M squared plus B squared minus 2BN plus N squared equals, and this side's supposed to stay the same, A squared plus B squared plus M squared plus N squared minus 2AB cosine theta. You can keep this the same. That's your dot product formula already. All right, now look at the things that can be subtracted off. Well, A squared is the same on both sides. That's gone. B squared, or well, M squared is the same on both sides. Subtract that off. And instead of just doing all the minuses, I'm just going to do this because I know I can subtract them off on both sides. So a lot of stuff went away right off the bat. Okay. Now, I have negative 2AM minus 2BN equals negative 2AB cosine theta. Now, again, I'm trying to solve for AB cosine theta. We are almost there. I'm going to divide by negative 2 on both sides to get it by itself. And when I do that, that goes away. I just have AM. That becomes positive BN equals AB cosine of theta. And if I go back and look, this is AM times BN. So really what's happening is I'm taking the x coordinates at the endpoints of these vectors. I'm taking those x coordinates, multiplying them together, add them to the y coordinates, multiplied together. So a more general way to show this, the dot product of A times B. And I know that's true because we found the dot product before as AB cosine theta. So this ultimately is the same thing as A dot B, not multiplication, but dot. So A dot B is equal to x1 times x2 plus y1 times y2. If you just have coordinates or vectors in component form, then you just take their x components, multiply them together, multiply the y components together, add them together, and that is also your dot product. Now, let's practice an example using the formula we just came up with. So I've got u and v, they're in component form. So if I want to find u dot v, I'm just going to multiply the x components together, add to that the y components multiplied together. And we get negative 4 plus negative 15, and then we get negative 19. And there we go. So deriving it took a while, but doing the problem is not too bad. Okay, so find the angle between these two vectors. This is something that's going to come up on the homework. It's going to come up from time to time throughout problems you do. And it's where you really need both formulas, both dot product formulas. So I know one way to get dot product. So let's do it this way, A dot B. One way to get that is to multiply these two together. So 15, multiply those two together, negative 48. And my dot product is going to be negative 33. Now because I know that A dot B is equal to the magnitude of A times magnitude of B times cosine of the angle, well, if I can figure out, I've already got dot product, if I can figure out these magnitudes, that's all I need to get the angle. So let's get the magnitude of A and B. So magnitude of A, well, we're just really doing a distance formula for it, so if it helps, if we want to start with the origin, we go over 3, down 4. So I'm going 3 and -4, and I find the hypotenuse of that triangle. So square root of 9 plus 16, because I'm squaring 3, squaring 4. That's square root of 25, so 5. If you recognize that to be a Pythagorean triple, then that's even quicker. For magnitude of b, same idea, went over 5 and up 12. I want to find the hypotenuse, so 5 squared plus 12 squared. That's going to be 169, which is 13. It's another Pythagorean triple. I picked those on purpose, but if you recognize those, great. If you didn't, that's okay, because you can just do the Pythagorean theorem and get there that way. So now I've got a dot product. I've got a magnitude for a and b, so now I can easily find cosine. So let's plug some stuff in here. We know the dot product is -33. And that equals the magnitude of a times the magnitude of b times the cosine of the angle between them. So for what's going to go in the calculator? Well, that's going to be 65. 5 times 13 is 65. So I'm dividing by 65. If it helps, think about dividing by 5 and dividing by 13, which again is 65. So -33 over 65 is the cosine of the angle. I'm going to need to find an arc cosine, and then I'll have my angle. We may need to pay attention to where the vector ends up in the end, so we'll come back to that if we have to. All right, so doing the arc cosine, I get an answer of 120.51. So the angle between these vectors is 120.51 degrees. Now, a few minutes ago, I mentioned that we may need to look at the quadrants we're in, things like that. So let's talk about that. What are the range of answers for arc cosine? Okay, so pretty quickly you should be able to tell me that arc cosine gives you an answer between 0 and 180. If we're finding the angle between two vectors, it's kind of perfect because 0 is as small as it can get, 180, and they're as far apart as they can go. They start coming back together if you go past that. So really, you don't have to worry about quadrants and things like that. When you take arc cosine, you're going to get an answer that is the exact angle between the two vectors, and you're done.